1, 2, 3. Can everybody hear me up there? All right, thank you. So here's a roadmap of where we are in the course so far. This is the Chomsky Hierarchy. We talked about it a number of times. So here's the picture, and now you can see this picture better. Because we talked about regular languages. This is the class of languages right there. They contain the finite languages. Every finite language is regular. But some languages are not regular. They're deterministic context-free, such as A to the n, B to the n. It's context-free because you can have a grammar for it pretty straightforwardly. But it's not regular because by the pumping theorem, you can prove it's not regular. It doesn't have a pumping property. We already proved that last week. And then the general context-free languages include non-deterministic context-free languages. Remember, non-determinism is essential in push-down automata. And so we've covered these regions of the map so far. So this is a Venn diagram. It's a set containment diagram. Right? Each class is properly contained in the class below it. So these are sets, and these are proper containments shown. At least most of them are proper containments. Some of them may not be proper. We don't know. Some of them are open questions. Whether P is equal to NP, that's an open question right there. But still, it's a subset. P is a subset of NP. So these examples in green are examples of languages that are in this class where they reside on this map or Venn diagram, but they're not necessarily members of the classes that are smaller than it. So A star is regular but not finite. Here's an example of a finite language, just A and a B, pretty trivial language. But A to the n, B to the n is deterministic context-free, but it's not regular, whereas WWR, palindromes, the language of all palindromes, is context-free but not deterministic context-free. And A to the n, B to the n, C to the n, we mentioned that language too a number of times. That's not even context-free, but it is recognizable in polynomial time. In fact, you can recognize it in linear time using a Turing machine. We're about to talk about that. And there's other classes here as well. We'll not necessarily go into each and every class on this slide. And by the way, there's many other classes besides the ones I'm showing you here. There's literally hundreds of classes that have names. And of course, there's an infinity of classes that don't have names. So this is a very, very simplified version of the overall picture. So you're seeing a very tip of a giant iceberg, infinite iceberg, in fact. But so far, we've covered this region here. And we're about to keep going up. And we're also covered a few languages that are outside that region. So for example, we covered a decidable language that's not necessarily polynomial time. We covered recognizable languages that are not necessarily decidable. So for example, a language is recognizable but not decidable is what? For example, I'm alluding to it here with a capital H. It's a big hint. A language that you can recognize yes instances of, but not necessarily no instances of it. The halting problem, right? So we mentioned that a number of times. You can tell if a program halts by just simulating it, but you can't tell if it doesn't halt by simulating it. Right? So the halting problem falls right in this region here. We'll talk about specifically recognizable versus decidable in great detail. Probably beginning next lecture. And the complement of the halting problem, H bar, the complement of the halting problem, it turns out it's not even recognizable. So we've also touched on some other regions here besides the ones down here. So how many understand this map, what it means, what are some regions in it, some elements in some of those regions? Okay. And this is a touchstone for the whole course. Right? This is called the Chomsky Hierarchy, pioneered by Noam Chomsky back in the 50s and built upon the 70s and the 60s as well. And it contains a lot of information. There's a lot of theorems that we proved already and around this region, and many other theorems that we'll prove still. Any questions about this? So I'm kind of showing you the bigger picture, kind of a, the roadmap that we've been following and we'll keep following. And occasionally, I'll keep showing you this picture once we explore other regions so that you always see it in context of where we are, where we've been, where we're going. Okay. So where are we going next? Well, we're exiting the context-free languages and going into things that can be done in polynomial time, and generally things that can be decided or recognized. So we're kind of going up to these two red regions. And we're going to skip some of those for now. We'll see if we have enough time to specifically cover other regions here. But next is we're going to the decidable and recognizable kind of realms, pieces of this big Venn diagram, set containment diagram. Just to be sure, each oval, each circle or region in this Venn diagram, in this roadmap, what type of object is it? Animal, mineral, vegetable, something else? Just a type. Each circle. It's a set. All right, let's dig a little deeper into the type. It's a set of what? What are the elements of each one of those sets? That is the region, many regions in this set of languages. And each language is a type. Set of strings or words. Strings, let's call them. So each circle here, each region here, I guess oval, or however you want to talk about it, each region in this Venn diagram is a set of sets of sequences of characters. Types are buried 4 deep here. How many get that? So keep that in mind. Each one of those things is not a set of strings. It's a set of sets of strings. Some of these subsets of strings are infinite, some are finite. But each oval here is an infinite set of sets. There are no finite ovals here that contain only a finite number of elements that are sets. Each class here is an infinite class, each one containing an infinite number of languages. Each language in itself might be finite or infinite, and most of them are infinite. And so these guys in green here are elements of these regions, but each thing in green here is an entire language, a set of strings. So I just wanted to make sure you wrap your mind very tightly around the types. Because if you lose sight of the types, if you lose track of the types, you have no hope of knowing what the value of these objects are, right? If you don't know if it's a mammal, you have no way of knowing it's a zebra. Because if you know it's a zebra, it's automatically a mammal. But if it's a mammal, it's not automatically a zebra. So if you don't know the type, you don't know the value of what it is you're talking about or referring to. So keep the types always very, very tight, nailed down in your mind. All right, so continuing up this hierarchy, let's talk about Turing machines. So a Turing machine is basically a finite automata with a tape, with a semi-infinite tape. So instead of a stack, we have a tape. So we have all the components of a finite automata still in a Turing machine. So on some of these components, most of these components, nothing much changes. You have a set of states. That set of states is finite, right? One state is distinguished as the start state. You have a tape alphabet, and you have blank symbols on the tape, so they can distinguish tapes symbols that you haven't touched yet from tape symbols that you've actually modified before. So if it's a blank, you know you haven't touched it, and you can overwrite a tape symbol with some other symbol. Just like in a stack, you can push and pop from the top, but in a tape, you can do it anywhere, not necessarily on one end or the other of the tape, right? So the input alphabet is still sigma, and basically we say that the input alphabet is all the characters other than a blank character, because the tape is mostly blank at the beginning. It's an infinite tape. You can go on forever, but you start at the beginning of the computation with the right-hand side or the left-hand side, depending on which point you want to point the tape into, which direction. And then, of course, you have a transition function. You have an initial state where the computation begins. That doesn't change, like a finite automata. You got to start the computation somewhere, and we started at the initial state, purple Q0, same as finite automata, same as push-down automata. And, of course, you have final states, and those are a subset of the set of states, same as a finite automata, same as a push-down automata, a set of final states. If you end up in a final state, you accept the string. If you end up the computation not in a final state, you reject the string. Where most of the action happens here is the transition function. Again, color-coded purple for delta. Delta means usually change or difference. So that's why we use delta for a transition function. It takes us from a state and a character on a tape. So this is the tape alphabet here, to another state, and you overwrite that character with some other character from the tape alphabet, and you go left or right. LR means either left or right, or you can stay put, let's say. So you don't have to go left or right if you want to stay on the same square that you pointed to right at this moment. Yeah.
What is the dash?
Here?
Yeah.
That's its set difference. So it takes you from a state that's not a final state. So it's Q minus F. And to be consistent, I should have made this F red, I suppose, to be color consistent.
But so you can't have transitions from a final state?
So once you enter a final state, the machine stops. So from there, you're not going to transition anywhere because you stopped. The computation ends. So computation is, say, defined to be over when you enter a final state, just like a PDA, push-down automata, did.
Even if there are input left?
So once you enter a final state, you could go left or right on that transition, but the computation is over now. So as you transition, you go left or right, but that's an entire, together, that's one whole step of the computation. You change a state, go left or right. As you overwrite the character that you just pointed to, that's one phase or state or transition of the computation. One more step forward in the computation. So this is just a technicality. You can define a Turing machine that halts on some other condition. What kind of condition? Like maybe it empties out the whole tape, who knows? Or some other condition. But we just define it as being in a final state. And that's why the transition function, once it's in a final state, Q minus F here, it ain't going anywhere, so you don't have to define it for that eventuality. And then you just accept the string that you were given to begin with before the computation started. That state, that string is initially in the input, which means it's at the beginning of the tape until some other point in the tape, and between those 2 points, the string resides there on the tape. That's how you get the string in the input. It's sitting on the tape before you start the computation. It's given to you by being written a priori on the tape before you start computing or transitioning states or doing anything else. Yeah. So the computation goes left and right. I'm going to give an example, in a second. But the computation, the read-write head, now it's a read-write because you can also write to the tape, not just read from the tape. You can go left, you can go right, move across the input, and even go beyond the input and store other things beyond the input because it's a semi-infinite tape. So it's like an unbounded array, if you will. Okay. Any other questions? So far, this is the definitions. So far, we haven't really done anything with these definitions yet. Yeah.
Didn't we do finite automata before that could go transition from a final state to something else?
Yes. And here, we have to do it slightly differently because he's asking, in a finite automata, couldn't you go from a non-final state to a final state? Yeah, you could. But a finite automata, basically, the way it operates, it keeps processing all the characters of the input one at a time until it reaches the end of the input. And then, whichever state it's in, it's either accept or reject. You can redefine a finite automata to accept, once it enters an accept state, and then ignore the rest of the input. No matter where you are in the input, you can just stop and say, I accept. You can redefine it that way. It won't be any different. It won't recognize any more or less languages than before. But because the finite automata processes a single character at a time, we define it to accept a string if and only if it enters a final state when it exhausts the input. So we force it to exhaust the input. Okay. For a Turing machine, there's no such thing as exhausting the input, because you can go left and right and keep computing. You can get to the end of the input and then keep computing other things over the input. Right? So for a Turing machine, we don't have the notion of exhausting the input and then being in some state, and that we just say the Turing machine basically doesn't enter a final state until, if it's good and ready to accept that string, and under no other circumstances will it enter a final state. In other words, it's a very deliberate acceptance at any moment, right? Because there's no notion of exhausting the input. You can keep going. A finite automata, when it exhausts the input, it's done. Because the classical definition of a finite automata, it doesn't go backwards. And there's no way of going beyond the end of the input. So when it reaches the end of the input, it's got to come up with a decision. So whatever state it's in, that's that decision, final or not final. Yeah.
In that case, is there some way to detect that the input has been exhausted? Is there some special symbol or characteristic?
Yeah, because remember, the alphabet symbol, the alphabet of the tape contains a blank symbol, but the input alphabet, sigma, doesn't contain this blank symbol that I'm calling beta here, the blank for beta. So one way, like you asked, to detect whether the end of the input has been reached is keep going on the input, do your stuff, but when you reach the first blank symbol, you know you're one character beyond the end of the input, and so you've exhausted the input, and then you can keep going. But now at least you know. So now you can change states accordingly and so on. Yeah.
So beta is used to describe no data on both the tape and in the input?
No, just on the tape. The input alphabet is sigma, right? Input alphabet is sigma, and sigma is the tape alphabet minus the beta. In other words, it doesn't contain the beta. It doesn't contain the blank character. So the input alphabet specifically doesn't contain blanks, and that's denoted by the minus sign right here. So the input alphabet sigma is the tape alphabet without the blank character in it. In other words, sigma doesn't have a blank in it. You can have other symbols in the input that can correspond to input blanks, but not to tape blanks. These are two separate matters. But let's just say the input strings do not have a blank in them. They're just characters from the input alphabet sigma. It's not worth belaboring too much over this minutia. Let's just go with examples, and then things will become clear. Any other points for now? Okay, so the Turing machine is simply the seven tuple, right? The finite set of states, the tape alphabet, the blank symbol, the input alphabet, the transition function, where you start the initial state, and then all the places you can end up the final state. So this 7 tuple completely describes the Turing machine. But often it behooves you to draw the picture rather than give the formal description. Same as finite automata and Push-down automata. You don't want to just necessarily list all the gory state transitions like symbolically, algebraically. You want to give a picture and maybe an English description. That's easier to understand. So here's an example that shows what we just talked about. So here's a Turing machine. This is the finite control of this Turing machine. So the read-write head goes from left to right. The input is here in blue. The input is 1, 0, 1, 1, 0, 1, 0. And here are the blanks that we just talked about a minute ago. All these are blanks all the way out to infinity. Of course, because you know it's blank from this point on forward, you don't necessarily need to list them all or even think about them all as an infinite set of blanks. Just saying it's blank from here forward, and you just remember that and know that, and that's fine. So the description is always finite, even though technically the tape goes on forever. And an input string is accepted if and only if the machine enters a final state. When it enters a final state, the whole thing is over, it's accepted. Right? And a Turing machine, we usually say it's deterministic. We'll talk later about non-deterministic Turing machines, and we'll argue that they're equivalent. We'll prove that they're equivalent to the deterministic versions. So whenever you have a non-deterministic Turing machine, you can always replace it by an equivalent deterministic Turing machine that does the exact same thing, recognizes the exact same language, no more, no less. And often I'll use this kind of picture to denote the Turing machine. That's the tape kind of, winding around, and there's the finite control, which is this notion here of the set of states and the transition function built into this finite control. So symbolically, this means that. Right? There's the tape, and there's the finite control, and the machine kind of goes over the tape back and forth, calculating away, changing states, and modifying the tape as it goes. And that's how a Turing machine works. And by the way, in the book, we're into chapter 3 now, page 140, 150 about Turing machines. So I urge you to look at the book in those pages. More questions? Yeah.
So the input is actually on the tape to start with?
Yes.
It's not a separate construct like it is in DBA?
Yes. It would be equivalent if it was a separate construct, if you have a separate tape for the input. So you can have two tapes, one for the input, and that's a finite tape, and one for the work tape, that's the infinite tape, and that's equivalent. You can show that that construction will do exactly what the other construction will do, and vice versa. Yeah.
Does the machine start with knowledge of how long the input is, or do you just have to figure that out?
There's no place where the size of the input is stored explicitly, but if you want to know how big the input is, go to the end of the input, and you can count until you do that, and then you'll know. Now, the word count here is a bit of a misnomer. Where are you counting? You cannot count arbitrarily high in a finite control or a finite number of states. So you have to write the count also on the tape. And that's that complicates things. But yeah, the length of the input is not stored explicitly anywhere, but you can figure it out if you wanted to, by going explicitly to the end of the input by looking for a blank symbol before you do anything else. And then you can work with that count or do something else. So a Turing machine is a very primitive model of computation. It doesn't do anything complicated in one step. Just like a finite automata, just like a PDA. It can change a state from one state to another state based on which state you've been, which input, which tape character you're watching right now with your read-write head. Like it's pointing to this red box right here to symbol number 6 on the tape, and it's not looking at any other symbol other than the one that it's myopically focused on right now, symbol number 6. And based on that symbol, it can change states, overwrite that symbol, and move the read-write head to the left 1 square or to the right 1 square or stay in place. That's all it can do in one step. Very simple, very straightforward, very narrow set of operations or options. But don't let that fool you. A Turing machine can do anything that any other computation model can do, including programming environments, operating systems, real computers like Dell's and Apple's and Microsoft, products. And so a Turing machine can actually play World of Warcraft with you, or run a Unix operating system, or play chess or Go to arbitrary degree of cleverness. It's the ultimate computation power that we know of after 80 years since Turing has invented it back in the 30s, right? 70 plus years. But that takes a lot of programming and a lot of states, and you have to make sure it does the right things, just like when you write a program, right? So when you write programs, you have just a few very simple operations. You have an assignment statement. Then you have a for loop. Now you could declare an array if you'd like. You have a while statement, an if, then, else conditional, but that's about it. You have between half a dozen and a dozen different types of statements, and that's all you got. But from that, you can write arbitrarily large, complicated programs that do arbitrarily sophisticated tasks, like self-driving cars, or video games, or an operating system for a smartphone, or anything else. It's millions of lines of code together give you arbitrarily complicated behavior from very simple individual components. That's what's going on here. This is like the ultimate extreme example of that. In this Turing machine model, there's not even arrays. There's not even an if statement per se. There's not even a for while statement. All it is state changes. That's all. But from that, you can construct anything else that you want. That's the whole point of the Turing machine model. It's the simplest yet the most complete, most powerful computation model that we've ever come up with. And we tried really hard to come up with anything more powerful. We couldn't find any. And a Turing machine can do everything that we know is doable, a Turing machine can do, however complicated. Now, I'm not saying that programming a Turing machine to run Unix will be fun. I'm not saying it'll be easy. I'm not saying it'll be quick. I'm not saying it'll run efficiently. That's not what I'm saying. I'm just saying it's possible for a Turing machine to run Unix. If you allow, a trillion states and a very complicated transition function and blah, 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 yeah, it'll do that. Question?
In the picture, so at the top it says that the tape is unbounded, but in that picture at the bottom, it looks like the tape starts with the input and then runs to the right. Shouldn't it also run to the left with more blanks?
It could, but it won't make a difference. And in about 20 minutes, we'll prove that that's not going to help. So might as well not have anything to the left of the input to complicate matters. So when you start, the input starts at, so when you start a computation, the read-write head will initially point to the first tape square, and the input will start right there. and that'll be the end of the tape, or at least one of the two ends of the tape. The other end doesn't even exist, right? So it can go on unboundedly. So for kind of normalization reasons, or for kind of standardization reasons, we sort of set the standard that the input starts at the beginning of the tape, the read-write head starts right there as well, there's nothing to the left, and go, you can compute now. That's all. It's just a convention, yeah.
Does that mean that it's possible for move to the left to easily go?
Yeah, so once you're at the beginning and you try to move to the left, the machine will hang. So yeah, but that's just a technicality, and you can easily avoid doing that. And you know, we'll talk more about that in a second, or other things like that as we go. All right, so let's see how a Turing machine can compute something. So let's take an example of a language that we know is not context-free. So we know a PDA can't do it. Anybody can think of a non-context-free language? Yeah. 0 to the n, 1 to the n, 2 to the n, right? So 0 to the n, 1 to the n, 2 to the n. We know that's not context-free. We mentioned it. How do we remember this? Okay, it's important to remember that. You can prove that using the more complicated version of the pumping theorem for context-free languages, but for now, just keep in mind that this is a good example of a language that's not context-free, but it is Turing computable. How? So let's put it on the Turing tape. So let's take an example of a language 0, 0, 0, 1, 1, 1, 2, 2, 2. So there's an example of a language, of a string from that language, right? And then the rest of the squares here are blank. I won't bother to write, you know, beta here for blank, but that's what blanks are. They're a separate character from the input. So in comes a string like that, and that's one of those strings in the language. How does the Turing machine recognize it? Well, you set up the finite control, the transition function, to basically check that the ones, the twos, and the zeros are in equal numbers. How do you do that? Well, short answer, you do it the hard way. You just do it the tedious, meticulous, unrelenting, foolproof way. Let me kind of run through it first, you know, a little more abstractly, and then maybe we'll harp on some more details. Find the first 0. At the beginning, it's easy because the finite control is pointing at that 0. That's where the input starts. Find the first 0, you're already there, good. Then skip over all the zeros until you hit the first 1. Check off that 1. Then find the first 2. Check off that 2. So now you've eliminated, by check off I mean like cross it out. We'll still talking about in a second about what it means to cross it out. So you can say, okay, cross out this 0, find the first 1, cross out that 1, find the first 2, cross out that 2, and now you've eliminated one triplet, 0, 1, 2. What do you do next? Take a wild guess. One word. Repeat, right. Start going back to the left, find the first uncrossed or unmarked 0. There it is. So cross that out. Keep going to the right until you find the first uncrossed 1. Cross that out. Then keep going to the right until you find the first uncrossed 2. There it is. Okay, cross that out. Repeat. Find the first uncrossed 0. There it is. Cross it out. Find the first uncrossed 1. Okay, cross that out. Find the first uncrossed 2, skipping over all crossed 2s, of course. Cross that out. Repeat. Try to find the first uncrossed 0. It ain't there. What do you do?
Accept.
Almost. You can't quite accept just this second. Why? Yeah, because there could be extra ones here that you may have noticed yet. So before you can jump to acceptance, you're about to accept, but not quite. You have to check that there are no more extra ones. And next. Can you accept now? There's no more extra ones? Not quiet still. What should you do? Check to see if there's no more extra 2s over here. And if you go past the 2s, see no more uncrossed 2's, and you hit the first blank now you can accept. Because now you know for sure that there were equal numbers of 0's, 1's, and 2's because you matched them up in triples tediously, meticulously, relentlessly, but in a foolproof way. That has no way of missing out strings that are not of this form. How many get this? It's not hard, it's just full of details. Just like a program. No line in the program is difficult by itself, or confusing, or obtuse, or subtle. How many get that? No single line in a program is complicated by itself. But guess what? You put 100 million of those together, and you got an operating system, or an online video game, or a browser, or a Google search engine, or anything else that you want, or a self-driving car, or an intelligent program that's smarter than us. That'll probably take 100 billion lines of code, not just 100 million lines, but that's okay. So that's kind of this phenomena is at the very core of computation and computer science in general. From simple, small parts, you build complicated and sophisticated machinery and mechanisms and algorithms, all the way up to and including fully intelligent algorithms, like the ones that are driving cars by themselves or doing recommendation, magic on Netflix to you, guessing, or more precisely, computing what you like and what you don't like, and be right 95% of the time. That's a lot of subtlety and capability from tiny little single individual statements or state transitions. Each one by itself doesn't do much. And that phenomena, building complexity from simplicity, is what permeates the entire universe. We are all examples of that. Take any one of your cells, any one of your neurons or body cells. By itself, it doesn't do much. It's just a little blob, a little sack of protein and amino acids that does a little bit of biochemistry. It doesn't do a whole lot by itself, but put 10 to the 15 of those together, and you got a human being. And that could do a whole lot more than any one of its cells. So complexity arises from simple components interacting in globally non-obvious, subtle ways. Right? Physics is that way too. Take one particle or one atom or one nucleus, and one proton or one neutron. It doesn't do much by itself. Right? But you put enough of them together, you got a car or an airplane or a human being. So this is kind of the phenomena. Simple things begin to compound, and before you know it, it has very sophisticated behavior. How many get this general philosophical trajectory or trend or phenomena? It's very ubiquitous to everything around us and to us ourselves. We are like that. Yeah.
Just to harp a bit on the details of that particular problem,
Yeah.
you're going to have to check ones and twos afterwards, don't you? Also have to check the order of the input before you go start counting them up and crossing them out?
Sure. So you want to make sure that there's no ones and twos out of order. You can do that before you even start. Before you even start the computation, it's a very good insight. He says, how do you know that there's no ones and twos out of order, right? You look for zeros and then blindly look for ones. How do you know you haven't skipped over twos in between the zeros and the ones, which shouldn't be there, because it should be only zeros, then only ones, and only twos in that order, but not interspersed, mixed up some other way. You can easily check that before you start, for example. Just keep marching to the right, flushing all the zeros. When you see the first one, keep flushing all the ones, making sure that there's no more zeros. Keep again going to the right, flushing all the ones until you see the 2, and then flush all the 2s, making sure at that point you don't see any more ones or zeros. Yeah, so you can make that check. But you got to do stuff like that to make sure the whole thing works in a foolproof way. And those strings will slip by you that are not in the language and cause you to accept. Remember, when you accept a language, you must do two things, and you must do them both. You must accept every string that's in the language. And what's your other obligation? reject every string that's not in the language. And that's just as important. In fact, that's sometimes more important. Okay? In a court of law, very similar situation. You're sworn to not just tell the truth. You have to tell the whole truth and nothing but the truth, and these are two separate matters. One is not the same as the other. And telling the whole truth and nothing but the truth is often more important than just telling the truth. Because by omission, you can do, weave all kinds of stories that you want. Okay. So as you go through life, you need to be aware of the news. That's a good thing. Be able to identify, news events. But you should also identify fake news and not believe that. Because if you believe everything people say and write and tell you, even though it contains some truths, it can contain all sorts of weird non-truths and fake news and falsehoods, and that's not good at all. Not for you and not for society. So, similar thing here. The machine needs to do what it must, but not do what it shouldn't. Very, very important. I can't stress that enough. I know I said that in the last lecture or last two lectures even, but I can't overstress that fact. Okay. Everybody good so far on this example? So how do you recognize palindromes? Again, the hard way. Match them character for character, mark them off. Let's talk a little bit, let's dive a little deeper into the details. What does it mean to cross off a character? Let's talk about that. So here I cross them off and it all seems reasonable, but there's no tape out here above this tape where I can put the cross characters in there. So how does that work? Just using state transitions, and what does that mean to cross off characters? Yeah. You can clear that section of the tape, but what do you clear it with? Do you want to just write blanks here? Because if you do, if you write blanks on the zeros and blanks on the ones, eventually you may get confusing, because when you start searching for, when you backtrack from here on one of the iterations and look for the first uncrossed zero, you'll just see a sea of blanks here, and you wouldn't know you're in the zeros or the ones. So you see what I'm saying? You have to be a little careful, but you're on the right track. What else could you do? Remember, you're designing this Turing machine. When you design a Turing machine, you get to choose the set of states. You get to choose the alphabet of the tape. You get to choose the transition function and all of its gory details. You're designing, you're the programmer. When you write a program, you get to choose what each and every line of code looks like. And if you choose wisely, the program will work very, very nicely. But if you choose badly, you'll have all sorts of errors and bugs and glitches. But you are the designer. You have ultimate power of what this thing looks like. So what do? You can
create a new symbol that specifically designates as Palindrome.
Yeah. So have another zero symbol that instead of being, so now we have, so the alphabet, the tape alphabet originally contained a 0 and a 1, but now it's going to contain this symbol, a crossed 0, and this symbol, a crossed 1. And we may even need other symbols. Let's see if we do or not. So replace this with a crossed 0. The cross is really on top of this 0. It's really just another symbol that you invented and incorporated into your transition function and tape alphabet because you chose to do that, to make this machine work, to recognize that language that you're trying to recognize. How many get that? Yeah, same for the ones. You're going to have a crossed 1, and you'll probably need a crossed 2, I suppose. Well, denote it this way. That's also in the tape alphabet. So the input alphabet is still just 0, 1, but the tape alphabet can be different than the input alphabet. The definition allows that. See, the tape alphabet is different potentially than the input alphabet. Of course, the tape alphabet must contain the input alphabet because the input is already on the tape before you start. So by definition, the input is on the tape, and its characters better be part of the tape alphabet. But these are all just minor technicalities, and when you cross these things, you substitute them with these crossed symbols, which are just new symbols. Symbols don't have to be named, right? You can just talk about symbol 1, symbol 2, symbol 3, and symbol 4, like the ASCII or the Unicode numbering of these symbols. So we say a symbol is an asterisk, or a symbol is a parentheses, or a symbol is an exclamation mark. That's just conveniences. So we don't have to say Unicode character 01157, and you just have to remember that that's an exclamation mark. That's not convenient, it's hard to remember, it's not mnemonic. So remember, there's nothing magic about these symbols. It's just symbol 1, symbol 2, symbol 3. By the way, what's the process called of naming the symbols just with numbers? One word. It's not complicated. I just want you to nail down that abstraction. What's that? Count it. And conceptually, what process is that? Mathematically, conceptually, set theoretically. It's a mapping. Keep going. It's all correct, but let's nail it. It's a bijection. Yeah, keep going. It's an enumeration, bijection, numbering, sorting. I just want you to kind of make a connection to a concept that we harped on many times before. It came up in both homeworks. Dovetailing. It's dovetailing. How many get that? It's dovetailing. So ASCII, Unicode, EBCDIC, it's all dovetailing. You go through a bunch of symbols and you're numbering them one up. That's exactly what dovetailing does. Except these are finite examples of dovetailing. It's dovetailing nevertheless. Nobody said that for dovetailing, it's got to be infinite. It's a process of matching objects with natural numbers. That's what dovetailing is, yeah.
Yeah, so it seems like really inefficient to do that because you're essentially every time you're checking input, you're permanently changing the input. And you can keep track of the indices instead. And then just every time you check a particular index, you can just take that out.
Okay, very good point. He's saying instead of crossing things out and changing the input, let's just keep track of the index. So say, now let's remember that this was the first 0, and next time it'll be the second, and next time it'll be the third, and go right back to the third without crossing and uncrossing. How many see the suggestions? Great suggestion. Let me ask you this. Where are you going to store this 3 and 4 and 5? That's the index.
So if we think about it like a computer, and I assume this would be like some sort of input, you would have another data memory or something like that.
Okay, good idea. If you have a data memory, you can store it in data memory. Where in this definition of a Turing machine do you see a data memory or registers or arrays or variables? You have to have a second tape, and even then, there's issues. But right now, it's one tape and just states and state transitions. So you don't have memory or variables or stores or database or any place else to store that count. If you could, it would be nice. And our machines, these Dells, these smartphones, these laptops, these tablets, do have lots of extra variables and disk and memory and RAM and registers in the CPU, but that's just a convenience. This is a stripped down model. This is a bare bones racing model, stripped down. Even the seats are not existing in this car. Right? Sometimes they strip down a car so you can get a little faster in a drag race by even yanking out the seats or anything that's not essential. This model is a stripped down model of computation. All the non-essentials are gone. There is no hard drive. There is no registers. There are no variables or arrays or accumulators and places that make it convenient to store counters and numbers and quantities. So it's a nice idea to try to take shortcuts, and you can if it works. But you have to abide by this stripped down model of computation called the Turing machine, and when you program it, you got to abide by what it has and what it doesn't have. Just like saying, if you're programming your iPhone for an app, and I say, okay, store it in the hard drive of your iPhone. Just store a file there. Well, the iPhone doesn't have a hard drive, a spinning hard drive. It has other memory things, but, and I can't say, so you have to respect what's there and work with that and not make up new functionality as you go. Now, it just so happens that if you had a hard drive connected to the Turing machine, or registers or accumulators or other places, it'll be equivalent to the original. And he mentioned very astutely, if you have a second tape, you can store it on the second tape. And in a minute, we'll talk about what happens if you have more tapes. Because you can modify this machine model of computation to have 2 tapes or 7 tapes, not just one. Or many read-write heads, not just one. Or allow it to be non-deterministic, not just deterministic. Or allow it to have arbitrarily complicated alphabets. Or even a 2-dimensional tape. You can have a tape that's 2-dimensional. You can go to the left, but you can also go up, like all the squares in the plane. And you can have that too. Or a semi-infinite tape, one in each direction. Both directions are infinite, not just to the right. It turns out all these things are equivalent to the first, and we're about to prove that. Yeah.
Just like a quick little thing about you wrote up there, the game that you pulled that mess, doesn't it also need two crossed out and blank in there?
You mean the two crossed out here?
Yeah, does that when you gamma you close the brace, it's a bit early.
Yeah, all the symbols will be crossed out, and by the time everything is crossed out in triples, you can confirm that they're all crossed out, and then accept if and only if there's no extra characters and so on.
I mean, that set you wrote for gamma up top.
Yeah.
That should also have two crossed out and blank.
Yes. So there's the two crossed out right here, and you're saying it should have a blank? Okay, good. Let's add that in. So here's our little beta or blank character. And two, yes. Okay. In fact, let's put the 2 over here, because that's where it belongs with the 1s and the 0s. Yeah, good. Thank you. Now you're getting it. So you can design the Turing machine to work however you want within the confines of the model, and then you grind it out, basically. There's no magic silver bullet to produce a Turing machine on the fly for arbitrary functionality, just like there's none in programming. If I say, write a program that does X, it plays tic-tac-toe perfectly, or drives a car without accidents, or that searches the web like a web browser, or a search engine, or write a program that plays Second Life with you, Second Life being the video game. There's no simple recipe to how to do that. Programs can be arbitrarily complicated. There's a heuristic that I can give you about how to become a master programmer. Here we go. Go to school. Study it for a bunch of years, really hard, and then you'll be a good programmer. And even then, you will still make a lot of bugs and errors and glitches, but learn how to debug and be familiar with all the tools. And then you can go out and write World of Warcraft or self-driving car codes or operating systems, and with the help of 1,000 other people, because these programs are really large. So study software engineering and all this, and that's what you're doing right now. Right now you're following this advice I just gave you. Apparently you already know it, because here you are, right, doing exactly what I just suggested. Other than that, there's no shortcuts that we know of. How to write arbitrary programs, how to make arbitrary Turing machines, or finite automata for that matter. These are all programming tasks. How many get that? Constructing these machines is exactly what programming is. In fact, it is programming. It's not just similar to programming, it's programming pure and simple on simplified models rather than the full-featured operating system that you're used to programming on so far. Now you're seeing the bare bones of computation, of computer science. This is the bedrock where it all starts. And all these machines that we've built, these Dell computers, these smartphones in your pockets, all of them are basically modified versions of this to make it more convenient and more fun and more pleasant and more efficient to program, but that's what they really are at the bare bones level. That's what they call theory of computation. That's why it's so fundamental. That's why you're all sitting here learning it, because it's good for you to know these things. It's illuminating and enlightening in all sorts of ways, abstract ways and practical ways, and even kind of everyday fun ways that, like, just be happy you don't have to program a Turing machine every time you write in C or C++ or Python, because it'll be a lot harder to do it on a Turing machine. Not impossible. Possible. That's the whole point of Turing machines. They can do everything those more complicated models can do with very, very simple definition. So computation by itself is not that complicated to define. And Turing was the first one to do it. That's why we call them Turing machines, because he first defined this machine model. He says to compute, all you need is just a bunch of states and a transition function and some characters and an alphabet and a tape. That's it. You don't need anything more fancy than that. You don't need silicon or plastic or transistors or a screen or a keyboard or a mouse or Wi-Fi connection. All that is just fluff to make things more convenient. And don't get me wrong, they do make things a whole lot more convenient if you got these features like hard drives and flash drives and, you know, super processors that have multiple cores and, you know, lots of, you know, computing power and registers and ALUs, you know, arithmetic logic units and blah, blah, blah. But they're not necessary. They're just convenient is the point. Okay. So this is very insightful what he's done. He's boiled down, reduced computation to its bare essence, and this is it on this slide. It's all you need. And to this day, we don't know of any more powerful computation model than that, simple though this is. Okay. Yeah. Is it possible to build a Turing machine within a Turing machine? Sure, you can simulate it on this tape. This machine can simulate lots of other things on this tape by the right encodings. Just like in your program, can you simulate a Turing machine in your program? Sure. And you can simulate your program in a Turing machine. So your Turing machine can simulate your program and simulates another Turing machine. That can in turn simulate another program and can simulate another Turing machine. Right? You can make it as convoluted as you'd like. Because it's all possible to do, and a Turing machine can do this. Right? Okay. So that's what we mean by marking things. It's just more characters in the alphabet. And there's no magic in the machine. It just does things the hard way, the tedious way, but the foolproof way, the way that works. And so you have to kind of, when you construct a Turing machine, make sure it does two things. Accepts all the things that it should accept, but reject all the ones that it should not accept, just as important. Because in your program, you have to do the same thing explicitly also. And sometimes it's implicit. If I say, write a program that prints prime numbers, and you say, okay, I write a program that prints all numbers. For I goes from 1 to forever, print I. I've printed all primes. What's wrong with this program? With these 2 lines of code. It does print all primes. You asked me to print all primes, I'm doing it. For I equals 1 to a million, print I. That prints all primes. What's the matter with this program? It also prints non-primes is the problem. I didn't tell you not to print primes. And you can say, well, you didn't tell me not to print primes. But now you're playing gotcha with me, right? Yeah, I didn't tell you not to print primes. I also didn't tell you that your program shouldn't play tic-tac-toe in between printing primes. And you didn't do that either. So if you start saying I have a right to do whatever, even stuff that you didn't tell me not to do explicitly, then why not have your program, you know, play Second Life while it's printing prime? Why didn't you do that? So now you're picking and choosing. The point is this. If I give you a task for your code to do, it must do that task, but it must not do anything other than what I told you. That's often implicit, right? It's like saying, you know, so your friend's saying, you know, I don't know, could you you know, use my car to go to the market and bring me something, you know, do me this favor. And you say, okay. And then you take your car and go on a long vacation to Alaska. And after that, you bring your friend that thing that they want from the market after 2 weeks. And you say, well, you never told me not to go to Alaska with your car. I went to the market. You asked me to go to the market, and I did. But you see, that's not reasonable to behave this way. It doesn't even make sense. So a machine, a program, an algorithm should do what it must, but should not do what it's not supposed to do or told to do or was designed to do also. It must accept what it should recognize, but reject what it should not recognize. Okay. So again, now we're in the chapter 3.2, and now we can start talking about enhancements to machines. We talked about multiple tapes, multiple heads. Let's just dive deeper into that. So what if you have a larger alphabet? What if the alphabet was only 0, 1, but you want a new machine with a new alphabet, A, B, C, D, instead of just 0, 1? You want 4 characters, not just 2. Does a machine with 4 characters, can it do more? Can it recognize more languages? Could it do more computations than a machine with only 2 characters? Let me say, yeah, more characters will get you more sophisticated computation. How would you say, no, it might be a little more efficient, but it'll be the same thing. Yeah, it'll be the same thing. Why is that? Because you can encode larger alphabets with smaller ones. You can encode an A with a 0, 0, a B with a 0, 1, and so on, and I'm color coding them. And on the tape of the simulated machine, if you have a B and an A and a D and a C and an A in this larger alphabet with this more fancy machine with a larger alphabet, on the new machine with a two-letter alphabet, you can have groups of two characters where 0, 1 represents a B, just like this encoding here, or dovetailing, if you will. The 0, 0 represents an A, and so on. So in this new machine with two characters can do the exact same thing that the bigger machine with 4-character alphabet can also do by a straight simulation. You just have to make sure the transition function is modified properly so that when you jump from a state to another state on a B, in the new machine, you jump from that state to this new state on a double transition, first a 0, then a 1. And so you got to map the transition function to incorporate these encodings, but that's one easy, straightforward way of doing it. And the new machine with 2 characters will do exactly what the old machine did with 4 characters. It'll accept and reject the exact same strings as the original machine. It'll have the same language. How many see that? You can do that. And in real life, we do that also. In fact, our machines, the ones that we build out of silicon and plastic and glass, use only a 2-character alphabet, 0 and 1. It's called the binary system, or the binary alphabet. But when you type on a keyboard, there's not just 2 characters, 0 and 1. Imagine what a binary keyboard would look like. 2 big buttons, a 0 and a 1. That machine would work just fine. How many see that? It'll just be pretty tedious to program. Imagine texting to somebody with just 0s and 1s, you know, and saying, let's meet at this restaurant at 5 p.m. Now, there's a lot of 0s and 1s. You can do it, is the point. I'm not saying it's convenient, easy, or fun. Well, it may be fun for a while, depending, you know, how geeky you are and what your definition of fun is. But at some point, it'll just be tedious. But these machines, they can be tedious. And they don't get tired, and they don't get bored. And they do exactly what you say, no more, no less. Just like your compiler, just like your programs. So you don't have to worry about hurting the machine's feelings and having it feel like it's wasting its time for you. That's the beauty of computers. They never do that. So using encodings, you can dispense with larger alphabets, and the machine model of a Turing machine might as well have only 2 characters, 0s and 1s. And of course, the blank is always there anyway. All right, what if you had double-sided tape? So what if the tape was infinite in both directions? And somebody asked that. Who asked that earlier? 2-directional infinite tape. Good. What if it was like that? Will that buy you any extra power? Is this a superpower? You know, could this, you know, Superman do what Clark can't, or what an average human being cannot do with this extra feature of double-sided infinite tape, infinite in both directions? And the short answer is no, because you can basically fold a 2-dimensional tape into a 1-dimensional tape in a very straightforward way that captures both infinite directions using only one infinite direction. So flip it over like this, right? And then double it up. So these 2 tapes now, the first and the second half of the tape get overlapped. And of course, we space it apart. Check out these PowerPoint animations. I'm very proud of them. This is how I spend my weekends. My gift to you. And of course, you got to flip them over. And it's dovetailing, right? How many see dovetailing going on here? We mapped the integers to the naturals here. Because you had the minuses and the pluses, and now it's just the pluses. Except you have to be careful that instead of the transition function going left to right once, it's going, if it's supposed to be going to the right, you have to go to the right twice. Because you're going from this 1 to this blue 0 to this next blue 0 to this next blue 1. Because that's what's happening here when you're going to the right on the machine being simulated. Right? So with that in mind, the new transition function adapted to this dovetailing scenario will also do the right thing and behave exactly like the old transition function do, and the machine will accept and reject the same strings that the old machines accepted and rejected, except now you're only using a single 1-dimensional, 1-sided infinite tape, not 2-sided infinite tape. So the point is, 2-sided infinite tape doesn't buy you anything extra. You can simulate it with a 1-sided infinite tape. So it's not a superpower, it's equivalent. Question? He's asking, is a Turing machine just, if a Turing machine can do everything that a finite automata can do, won't any enhancements to it not increase its power? Well, but for finite automata, some enhancements did increase the power. Right? If you had 2 heads, for example, for a finite automata, you can recognize 0 to the n, 1 to the n, that a regular finite automata with 1 head cannot do. So first, you have to be careful. Some enhancements enhance a certain model, and the same enhancement may not enhance another, and vice versa. So it's not equivalent to finite automata. In fact, a Turing machine is a finite automata with a tape, or conversely, a finite automata is a Turing machine without a tape. Just like a PDA was a finite automata with a stack, and a finite automata was conversely a PDA without a stack. But when you have a stack, you can do more things. When you have a tape, you can do yet more things than with a stack. Yeah.
Is an oracle an enhancement for a Turing?
He's asking a subtle question. Is an oracle an enhancement? The short answer is yes. If you have an arbitrary oracle, a black box that you don't say anything about except how it behaves, but you don't even say what algorithms are inside, just the output-input behavior, yeah, that can enhance the power. Because they'll be like imbuing your superhero in the movie with magic. Once you say, okay, the character has magic, all bets are off. You can change humans to frogs, and you don't have to explain how. It even defies conservation of mass. You know, where does 150 pounds become, you know, a 2-ounce frog? Where's the other mass go? You don't have to explain that. You're breaking laws of physics left and right. That's okay. Magic can do that for you by assumption. Same with miracles. Same with arbitrary, you know, inventions that you concoct, right? But algorithms don't work that way, and neither does physics or science, for that matter. You have to account for things and explain things, and not just state them, walk away, and have no responsibility. Okay, so by dovetailing, one-sided infinite tape suffices. Just make sure the transition function does the right thing. So if you're going here to the right, here in the simulated machine, you're jumping 2 at a time. How many get that? And if you go here to the left and you hit the red ones, which are the left of the origin, so the origin is like where this green is. If you start going to the left here, what are you doing here as a consequence? You can go to the left on the zeros, jump 2 at a time, but then you reach the beginning of the tape. So what do you do now if you want to continue to go on the reds here? You switch the parity to the reds, and then you jump 2 on the reds in between the blues, and you just keep in mind in your finite control that now you're in the original one going left below the origin to the negative cells, if you will, or at least the ones to the left of the origin cell where you started the computation in. But all that can be tracked in a finite control with more states and so on. It'll work. It'll be tedious, yeah. All these simulations are tedious, but machines can't get bored, upset, you know, or resentful of you if you make them do extra work, right? That's, again, an advantage of automata. They do exactly what you say, exactly how you say it. That's one of the things, you know, you learn in a subtle but very dramatic way when you first begin to program, that everything the machine does, absolutely no exceptions, is exactly what you told it to do and exactly how you told it to do it. It follows you to the letter. So why is programming so frustrating sometimes? You begin to learn how imprecise and vague your mind is. How many understand what I just said? Yeah, and that's a beautiful human revelation. You know, we think we are precise and say what we mean and mean what we say, and on a good day, you may muster that a few times. But in general, our minds are, you know, a big mush of proteins. And it's amazing that they work on an average day. In fact, for a lot of people, on an average day, not so much. And if you read the news, there's people who do crazy, arbitrary things, even violent things, because their mind can't wrap very tightly around rationality and self-awareness and so on. So, but I digress. The Turing machine does exactly what you say, exactly how you say it. So you have to be careful and just wrestle it to the ground, just like you would with a compiler or a program, to make sure it does what you want. All right, what if you have multiple heads? We already saw that the finite automata with multiple heads can recognize 0 to the n, 1 to the n, which is not regular. How many remember that? All right, let me repeat that. A finite automata can recognize 0 to the n, 1 to the n. 0 to the n, 1 to the n is not regular. It's context-free, but it's not regular. But a finite automata with 2 heads can recognize 0 to the n, 1 to the n. You start at the zeros with one head, the other head you push to the first one, and then you lockstep, single step, through all the zeros and all the ones until you exhaust both, and then you know you have a 0 to the n, 1 to the n in your hands, as opposed to not, and you accept if and only if. How many get that? Okay, that's better. And so what about a Turing machine with multiple heads? Can it do something more, like I just said? It turns out that for a Turing machine with multiple heads, you can do the same thing with only one head. Take these three heads that are blue, green, and red. So the three heads can independently move. Each one can independently move left or right. So we're extending or enhancing the basic model to have now three heads, not one. So will that get you an extra superpower? Not really, because you can simulate three heads with one head. How? Let's say you're doing a simulation step where you want to move these three heads. So first of all, instead of having a little b, have a capital B, and you get rid of this red head, read right head, by having the little b be a capital B. So it encodes a B in that location, but it's a B capital, which means it's sure enough a little b, but the capital B means the red head is on pointing to this location. So it's a little b with the head pointing to it, which makes it a capital B by increasing the alphabet size. Okay? And similarly, this little a becomes a capital A, and now I can get rid of this green head here, right? Get rid of that. And then this little b becomes a capital B, and this head could be gotten rid of, right? And once I get rid of all three heads, this tape here encodes exactly this tape up here and its three heads, but having only a single tape and a single head. How many get that? Now, how do you compute using this simulation? Well, if this head here wanted to do something, this will do it too, but the long and a tedious way. So for example, if this head wanted to go one to the right, this big head will find the first, where the capital B is, change it to a little b, move one to the right, whatever character is, change that to a capital, and then move all the way back to the beginning just to simulate one little tiny step of the original machine. And to simulate the other two heads now, it has to do it again 2 more times. How many get what's going on? And the point is, this simulation keeps track of this simulated machine, but it's doing it with a single head, plus a larger alphabet. Now, what if you didn't want the larger alphabet? You didn't want capital letters. You just wanted an alphabet of size 2 again. What would you do then? Short answer, do this. We already saw how you can simulate the larger alphabet with a smaller alphabet of only size 2. So you can compound and compose these simulations, and once you have a simulation that works with a single head but with a larger alphabet, you can now hit it with another simulation on top of that that will simulate this larger alphabet with an alphabet of size 2, same as the original machine. So you can compose these simulations or these techniques. How many get that? Okay, good. And this is called programming. Really what you're doing is you're programming these machines to do the right things, and you wrestle them to the ground, you beat them to the ground, you make them cry uncle and do exactly as you say, the hard way, one tedious step at a time. There's no magic here. It's just mechanism and details. Yeah.
So do we think of those other right heads as like pointers, and then the black right head is kind of like the program counter?
You can think about this as a program counter, but it's a little dangerous because the program counters can jump around to arbitrary locations. This just moves one to the left, one to the right. So it's a very restricted program counter. If you want to say that, feel free to say that or think that. It's helpful. Just don't carry that analogy too far so it starts breaking down. Okay. All right, more enhancements. What if you have multiple tapes? What if you have 3 tapes, right? Earlier we said, what if you have a second tape and you can store stuff to the second tape? It will make things more efficient? Yeah, it'll be more efficient. Will it do things that the others can't do? No. It won't. Because you can take these 3 tapes and simulate them with a single tape. How? Take these 3 tapes, stretch them out like this. You want to see it again in instant replay? Think about how long it takes to create these kind of simulations, animations. And now every tape is the blue tape is every 3rd character in blue, the red tape is every 3rd character in red. They're interlaced. What technique is this, by the way? Dovetailing. How many see dovetailing in front of your eyes? Good. Now you also know this meta recognition of why we harp so much on these fundamental techniques at the beginning of the course, dovetailing and diagonalization and proofs by simulation and power set construction and cross-product constructions. These will come up again and again, as I promised they will. So dovetailing will keep coming up. All right, so basically you can simulate these 3 tapes with 1 tape, just make sure the transition function doesn't get confused about which square is which tape, which cell belongs to which tape. And you can simply do this by jumping 3 at a time instead of 1 at a time. That's easy to do. Make every transition like a triple transition and keep track of all 3 tapes with a single tape and keep going, right? So multiple tapes don't add you any superpower. They just makes things a little bit more convenient, sure. So we design a Turing machine like an exam, or feel free to use 2 or 3 tapes if you'd like. Or using JFlap, there'll be an exercise, homework number 4 probably, to write a Turing machine using JFlap, do something simple. If you want 2 tapes, fine, have 2 tapes. And now you know that 2 tapes are not better than 1, and 2 heads are not better than 1 either, but for finite automata they are. More enhancement. What if the tape was 2-dimensional? If the tape was 2-dimensional and you had arbitrary number of rows, and each row was infinitely going to the right in terms of size, and would a 2-dimensional tape get you anything more in terms of recognition power? And the short answer is no. You can flatten it. Here's flattening the tape. Take every row of the tape that's not blank and write them all one after the other in serial, and make sure you separate them with some character in the alphabet that's new, like a $sign, to make sure you know where one begins and one ends. And so you know this is the first row, that's the second row, that's the third row. And when you simulate a machine here, let's say you have the read-write head points to this square, and you want to go to the left or to the right, all you're doing is going to the left and to the right here. But if you want to go up or down, it's a bit more complicated. You got to jump over here or jump over there, and you have to count how far in you are and how far you should go into these other 2 regions. Let's say the blue if you're going up. So if you're on the 4th square and you're going up, you want to count this 4, count 4 in here, and then you'll be on this one here. How many get that? And you have to do it the tedious way by marking, just like we did on the board earlier. But it's doable. So you have to mark and unmark a whole lot just to go 1 square up in this 2-dimensional tape. But the point is, it's doable with a single 1-dimensional tape, so it's not a superpower. Okay? And similarly for other, and by the way, this is how compilers implement 2-dimensional arrays. This is called row major order. How many have heard of that or seen that? Good. Now you know how 2-dimensional arrays are implemented inside your compiler, inside your operating system. There is no 2-dimensional, 3 or 5 or 7-dimensional arrays in your computer. It's implemented using, what is this technique? Dovetailing, thank you. And now you know how compilers implement higher dimensional arrays using a 1-dimensional memory, which all computers have 1-dimensional memory when you purchase them in a box. There's no real 2-dimensionality there. Yeah.
Strictly speaking, when you're trying to collapse what is supposed to be infinite 2-dimensional space into 1-dimensional,
Yeah, so he's saying, shouldn't you dovetail diagonally? But here, the nice feature is that beyond a certain point of every row, the rest of the row is blank. And because it's blank to infinity, you don't have to store all this infinite number of blanks. You store 1 and you say ... or the rest are blank. So you only have to store the non-blank portion of every row. And that's easy to do with $signs, separating them. And you don't have to go to infinity, and you don't have to diagonalize. You don't have to dovetail on the diagonal, which is more tricky, although you could have done that too. It'll just be trickier. All right, any other questions about that? And next time we'll see other enhancements that don't change the power, like non-determinism, doesn't change the power, or you can do any combinations. You can have a machine that's non-deterministic, 2-dimensional tape, multiple heads, multiple tapes, multiple alphabets, and you can compose these simulations, and nothing adds to the power. So bottom line, Turing machine model is the most powerful one we know. We have no way of increasing its power, which means it has the ultimate power. And we'll talk more about that next time. All right, see you then.